Exercise 128. Let's prove that Yoneda embedding preserves limit. So we have done exercise very similar like this, and we have used this fact to prove the limits, commutes with limits, and the sub-exercise. But now let's discuss this. So what do we have to do? So you need embedding. Let's say you have a category C. Do you need embedding? Let's denote by HC to from a category C to the category of functors, from C up to the category of set. Map any object X to home, so to H of X. So why not just call this H of X, which is home comma X from the category home in the category C. Now suppose we have a limit in C, so which means we have a diagram. Let's say D. Let's say of type I. So you have a functor from I to C, and then you have limit. Why not just let me like this, I, and then you have a limit AI. This is a universal code, and then you apply the functor H. Here you have a diagram. Let's call this, if you call this D, diagram D of type. This is diagram. Let's call it HD. And this is I to say to set of C up. Here we compose with H. And now the question is this again the universal cone, right? So the first attempt was that. So I was trying to use the fact that, so this is in the category of C, trying to use the fact that this is the same as home AI, which means if we know that the limit exists in this category of set C up, then this is telling you that I could define the limit to be this one. Well, this was not quite true. What you really have was that for any object, let's say for any object, let's say t test. For any object t, we have this isomorphism as set, right? Both sides are in the category of set. This is bijection. This is from the, I call it a remark or fact. This is from the by the property of limit. We know in the category of set the limit exists, and here we know that the limit of AI exists. This is by our assumption, and so we have this. So now suppose you have a functor in set C up object here with commutative diagram. The question is that this factor through this, and so by universal property this is the limit. So the argument is that for any object t, let's say C up, we have this n of t, a set, and then the commutative diagram is telling you that it is a cone over this diagram, right? But then by the universal property of limiting set, we know that there's universal cone over this diagram, which is the limit of this, and so it factors through this. This is telling you that conclusion is that for any t in C up, we have nt, let's call this eta t to by isomorphism to the home of t lim IAIC, such that diagram is commute. Such that for any AI, so this is commutative. But to check this is natural transformation. To construct natural transformation is not sufficient to just look at one object, right? What we want is for any, let's say T1, T2, in C up, and so in other words, T2, T1 in C. Do we have those are covariant functors from C up to set? Yeah, so actually still this direction. Do we have this? So this we have. Similarly, we could construct eta up T2, right? And then the question is this commutative? call this F. So this is composition with F. So you have T2 to T1, T1 to we map T1 to with composition with T2. So like this. Right. This is N of F. In other words, it's kind of like let's still look at eta T1. So eta T1, you could think of it T1 by the universal property. We got a cone with T1. AI. T1 lim AI. This is the universal cone. We got this eta T1. The question is, what do I still have a commutative diagram? So actually there is this unique, right? The question is, can I put instead of eta T1, but I put this, let's call this, could still call it home F. Actually it's home F lim. It's just for short. Can I put there, making diagram commutes this composition? So wait, not sure. I'm not sure I can do this. Let me think. Let me think. So can we see? So the question is now sub-exercise. Is eta T a natural transformation? So what I want to say is that, what in my mind was that if you have an T1 and T2 and F, so you still have commutative diagram because our n is given as like a cone factor, so which means here you map to home, let's say h of T1 diagram, here's a cone to h of T2 diagram, and then you have this yes, so yeah, not very actually what I should put here, let me put it more accurately. Home T1 AI, home T2 AI, and here you have the lim home T1 AI, universal cone, home T2 AI, and by isomorphism this is the same as home T1 lim AI, home T2 lim AI universal cone, and then there is a connecting morphism by home f lim AI, and then here we have this eta T1. Here we have this eta T2. The question is the diagram commutes, right? Yes. Yes. I guess here we should involve also the commutative the diagram here. Let me see whether I could write this more clear. Theta T1. Let me just pick one of it. Let's just pick this home T1 AI. So this is commutative diagram. Then here eta T2. Home T2 lim AI. Home T2 AI. Diagram commutes. Here we have diagrams. Let me write also one more. Let's say home T1AJ. Making the diagram commutes. Making the diagram commutes. Diagram commutes. So this is saying that I'm still making the diagram, sorry. Still making the diagram commutes. If I look at this, right? Still making the diagram commutes, so which means this, by the universal property, this one still factors through. Universal object in a unique way. But then you know that the composition of this with this gives another map at this, saying that this is commutative, but there is a unique one map. So this one must be commutative. Or more precise, there is a unique one making the diagram commutes. So this one making the diagram commutes, which means this should be the same as this, but this is because we know this is commutative, and then composed with the same one, it's again commutative. And so this one making it's the one making diagram commutes, so we should be the same as this one. Similarly, if we want to check this also commutative, what do we do is that we claim that we claim that this also make that diagram commutative, because so we come here and here, come here and here. Now the commutative diagram you want to check is this. This is what you make diagram commutative. So let me change the color. So now let's check to make the diagram commutative. Sorry, did I change the color? Change the color. Pink. Or overlap it. So you're still looking at this, 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 this. This is how you make the diagram. Commute, making yourself a cone, and then by the universal property, there should be a unique map here to the universal object. And now I'm claiming that this way is also a map making the diagram commute. That would mean that what we have to check, is that this, and then, for example, here is the same as this, right? How do we do that? Obviously, we still have to use the information on the left hand side. So let's connect those. So if you have T1 from T2, let me make sure we don't mix the arrow. So this is in C from T2 to T1. And so if you have in C T2 to T1, then you could simply compose with, got a map here just by compose with F. Sorry, compose with F, right? You first from T2 to T1, and then you apply your previous one. Good. And you have this commutative diagram. Have this commutative diagram here. And so now what we want to do is that we want to use we want to check that just describe diagram commute, but what can we check is that we know that this is the same as this. And so the question is now, I mean, wait, why not let me just say that I'm still starting here, but this time I'm going to go this way, this way, this way, this way, and this way, and so making the diagram commutative. And so this is a cone over this diagram. And so by universal property, there must exist a unique map here, making the diagram commutes. There should be some art of drawing diagrams to make what you want to observe more clearly. I mean, the art of drawing diagrams. I'm drawing this for the reason positions. Make this not very obvious. Let me think for a while. For example, now this diagram should make which diagram commutes. So this is making this commutative, right? And because this is commutative, this is also the same as making this commutative. And this is actually saying that this one is the same as this one, because there is a unique one, making that commutative. But seems it's finished, but actually not yet, because the red bar here and the green bar here, why should they be the same? Because I'm making different diagrams commute. They are the unique bars such that which diagram commute, but they are making the different diagrams commutes. Why that two slash arrow should be the same? If you want to prove that the same, you have to say that the red bar also make the green diagrams commute, or the green bar also make the red diagrams commute. So the question is this commutative? Right? Is this commutative. And the way we do that is we look at here. This is the same as x2, the commutative of this. This is the same as this, 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 this. And then that should be commutative. Let me repeat. This should be a commutative diagram, because n is a functor which have natural transformation into this diagram. So in particular, when you take T1 to T2, we know this should be a commutative diagram. Let me put in different color. Let me use blue. I mean this one. Let me put in a color shadow. Not a good idea, I think. I mean, this one. This is a commutative diagram because this is a natural transformation from n to home bar AI. As I said, this is commutative, will tell you that this is commutative, and they will then tell you that this is commutative, and then tell you that by the definition of the red slash, this is commutative. But if this is commutative, then there is a unique one, or the green one, or the green one, already making that unique commutative by the universal property of this. And so the green and the red one must coincide. I think this is okay, but it took too long time to prove this. Seems very tricky. So I'll finish the proof. This is indeed a natural transformation.